This is a facial recognition algorithm that I was able to create completely from scratch just using Python. It works by scanning each image for tiny micro patterns. These are kind of like tiny fingerprints in the image, and it determines a match by finding the image with the most similar micro patterns. The images on the right are being shaded green when these micro patterns are similar, and the images are shaded red when the micro patterns are considerably different. The official name for these micro patterns are local binary patterns, which I'll go into more detail later, but for now, just know that this is what we're scanning for. And ideally, we want these patterns to be the same. But when we do find differences in our scan, we update this distance metric so that we have an overall measure of just how different these two images are. Now, if you're like most people, you might not know anything about facial recognition, and it might feel kind of like magic. But if you bear with me, I think you might be surprised to see just how understandable it is, as I believe that the average person watching this can walk away with a very deep understanding of how facial recognition can work. To start, we're going to use a single image and we're going to try to extract micro patterns from it and use them to create a kind of digital fingerprint for the image. Though instead of this normal photo, I think it'd be really helpful to start with something much simpler. Here, we have an incredibly low resolution image of a person's face. It's a 13 by 9 grid, giving us 117 pixels in total. I believe this simpler image is going to make understanding this algorithm much easier. Now, the very first step of this algorithm is to make this image black and white, which loses us information right off the bat. But notice it doesn't lose us any information when it comes to the patterns in the person's face. And I can't emphasize enough that patterns is all this algorithm cares about. Next, we're going to extract a local binary pattern. And to do that, we're going to zoom in to this 3x3 grid of pixels. Now, this is about as micro as we can get for a pixel, while still considering how it relates to its neighbors. Here, we have what's called a local pattern. This is one of those micro patterns I've been referencing so much, and our goal is to somehow capture the essence of this pattern in a numerical way. The reason we want a number to represent this pattern is so that we can easily compare it to other patterns in a way that isn't visual, something that an algorithm can understand. And for this, nothing works better than a number. The nice thing about digital images is that each pixel already has a number associated with it. And for a black and white image, these numbers range from 0 to 255, depending on how bright that pixel is. The brighter the pixel, the higher the number. And now that we have these numbers, we can now manipulate them to form one number. First, we're going to take the center pixel and compare it to each of its 8 neighbors. Here we are just subtracting the neighbor pixel's value from the center pixel's value. Now we change each negative number to a 0 and all other numbers, including 0 itself, to a 1. Now we have 8 ones and zeros, and notice how a 1 means that the center pixel was as bright or brighter than that neighbor. And a 0 means that the center pixel was less bright than that neighbor. Now, starting with the number in the top left and going around clockwise, we can order these new digits to form a binary number. And this binary number still has encoded into it how the center pixel relates to its neighbors. Again, a 1 meaning that it was as bright or brighter than that neighbor, and a 0 meaning that it was less bright than that neighbor. This binary number, by the way, is where the binary and local binary pattern comes from. We can then convert this binary number to a decimal, giving us our LBP value. And the nice thing about this number is that it uniquely identifies this pattern, at least in terms of how the center pixel relates to its neighbors. And this is great because when we scan an image and we see the number 254, we know that this pattern shows up in the image somewhere. Going back to our original image, we can repeat this process for every pixel, which gives us 117 total local binary patterns, which is a complete list of all the micro patterns in the image. We can rewrite this list as a tally, which shows us how many times each pattern appears. Now, the biggest number we can have to represent a pattern is 255. And the reason for this is because that's the biggest number we can get using 8 binary digits. And this is true for any image, even if it had thousands of pixels. As such, we can use this tally to create a histogram where the x-axis goes from 0 to 255, and the y-axis is the number of times that pattern appears in the image. And the nice thing about this histogram is that it completely captures all of the micro patterns found in the person's face. You can think of this histogram as a kind of digital fingerprint for the person's identity, which by itself is awesome. But perhaps the best thing about this histogram is that it is pretty resilient to change. Let me show you what I mean by this. Let's consider variations of this photo, such as when the person is angry or when he has his mouth closed. If we perform the same exact process and extract the local binary pattern histograms, they look like this. Notice how remarkably similar these histograms are. At a glance, they look the same. And this makes sense because while some of the patterns are definitely different now, most of them have stayed the same. Taking a closer look at our original image and the one with his mouth closed, we can notice that the histogram on the right has a lot less patterns appearing in the lower numbers, patterns that have been lost by him closing his mouth. But since both histograms have 117 values, this just means that these patterns have moved somewhere else. In particular, a lot of them have moved here. Now, this resilience to change is important because sometimes in photos, people have their mouth closed or maybe they're angry. But in those cases, we wouldn't want our digital fingerprint to change too much. We'd want it to be similar. We'd only want substantial changes to the histogram when the person in the other photo looks totally different. Now, these patterns are exactly what the algorithm at the beginning of the video was scanning for. But the last step of this process is getting that distance metric, which means we need the distance between these two histograms. Because while it's nice to be able to tell visually that the histograms are similar, our algorithm is going to need something precise. It's going to need a number. Fortunately, there are a lot of equations we can use to get the distance between two histograms. And to be honest, a lot of them would work well here. But for this video, we are going to focus on the chi-squared statistic. And while this equation might look daunting, trust me, it's not. For each bar in our histogram, this just takes the difference in height for that x value and squares it. Then it divides by the sum of those heights. So for example, both histograms have a value of 2 for the pattern represented by the number 0. Plugging that into the equation, it gives us this. Of course, when we calculate this out, we get 0, since 2 minus 2 in the numerator gives us 0. This means that this bar has a distance of 0 between the two histograms, which makes sense because they both had the same value of 2, meaning that the pattern showed up twice in both images. Using a different bar as an example, like this big one, we see that the first histogram has a value of 43, and the second histogram has a value of 49. Plugging these two into our equation gives us this. And typing this into a calculator, we get 0.39. And this gives us a non-zero distance for just this bar, which makes sense since the numbers were different. Now you might be asking, what do we do when both bars are 0? Wouldn't that mean that we divide by 0 since their sum would be 0? Well, in that case, you don't need to apply the formula. Since both of the bars are the same height of 0, you can just say that there's no distance between them and give them a distance of 0. If we apply this formula to all of the pairs of bars and add up the distances we get from them, we get a total distance of 5.45, which for this algorithm is very small, which is a good indication that the photo is of the same person, which is really good in this case since the only difference between the two photos was a closed mouth. For comparison, if we apply the same distance measure between this image and the angry face image, we get a distance of 13.65, which means that this image is even more different despite the mouth being open. If instead we change the shape of the head entirely and perform our distance calculation, we get a distance of 21.02, which, as you'd expect, means that they're less likely to be the same person. And if we take the new circular head and close his mouth and make him angry, we get our biggest distance yet of 32.18. And obviously, that makes sense since this photo is indeed the most different out of the ones we've seen. And this is great because, as promised, now we have an algorithm that allows us to get a distance between two photos based on how similar their micropatterns are. And this is the full local binary pattern histogram algorithm. And now that we've covered it, we can now move on to these more complex pictures. Repeating the same process of gathering all the micropatterns in these images, we get these histograms, which now show us thousands of micropatterns. Notice, however, that there are still only 255 bars in each histogram, as there are only 255 pattern classifications in each image. As such, we can find the chi-squared distance by adding the distance between each pair of bars together, and doing that, we get a total distance of 2045.99. Now, these photos are of the same person, and if we check this photo against a different person, like this one, we get a distance of 3,943.30, which is indeed a higher distance, which is great because in this case, our algorithm worked by saying that the two similar pictures were of the same person. But now let's take a look at this pair. These two are also of the same person. Calculating their distance gives us a total distance of 1,724.63. If we change the photo on the right to a different person, however, and calculate the distance using this method, the distance shrinks to 1,150.71, which is not a great result since it's a different person, but with a smaller distance. Well, no algorithm is going to be correct 100% of the time, so to get an idea of how effective this algorithm is, let's run a test. For this test, we're going to consider 5 different people, and we're going to have 2 sets of photos for them. The first set is the sample set. Here, we're going to have 30 photos for each person, giving us 150 photos in total. This set is going to serve as our identity library, where these photos already have identities confirmed for them. And the second set is our test set, which has 5 photos per person, giving us 25 photos in total. This set is going to be used to test our algorithm. We're going to do this by using our algorithm to compare each photo in the test set with every photo in the sample set. Whichever sample photo is closest in distance to our test photo will determine the identity of that test photo. And our algorithm will be graded based on how many test photos it's able to correctly match. Using this algorithm locally, exactly how I have explained it so far, it gets 10 of the photos correct, or about a 40% accuracy. Now, if the algorithm were to guess an identity randomly, it would be correct about 20% of the time, since there are 5 options here. So this is an improvement from guessing, but for me, it does feel disappointingly low. Fortunately, we can do much better than 40% by implementing 2 relatively simple improvements to our algorithm. You see, when we were using the simpler image, we had some advantages that we lost when we scaled up to the more complex images. This section, for example, is a single pattern in our histogram, and this pattern alone gives insight into 8% of the photo, which is almost a tenth of it. That's a lot of insight to get from just one pattern. They cover a ton of area when it's a photo of this size. Also, patterns have a lot of uniqueness to them when they're in a photo like this. Take these 2 regions for example, where the center pixel is the person's pupils. These are the only 2 pixels that had a pattern value of 0. making checking for these values a lot more informative here. Looking at more complex photos in comparison, I'm going to highlight the pixels that have a pattern value of 254. And as you can see, there is a lot of them. First, notice that each pixel takes up a tiny portion of the image, meaning we don't get as much information from the pattern that is around the pixel. But much more importantly, notice how this pattern has no sense of uniqueness whatsoever. Like, notice that this pattern appears more frequently in this section for the photo on the left. However, when looking at this section of the photo, we see that the photo on the right has this pattern appearing more frequently. This leads to a weird situation where the number of times this pattern appears is actually similar for both photos. It just appears in different areas. But our algorithm does not care where the patterns appear. They just care how many times it appears. Also, take a look at this region, where we see this pattern appearing more for the photo on the right, which in this case brings the distance closer. But if you think about it, these patterns shouldn't even be considered at all. If we get the chi-square distance for just this pattern between these two photos, we get a measly 6.06. Which is nothing considering the pattern appears about 500 times in each photo. Our algorithm is comparing apples to oranges here. So the first trick to improve our accuracy is to force our algorithm to compare apples to apples. We want to force it to compare the same sections of the face. To do this, we can divide our photo into a 7 by 7 grid of equal size like this. Then we can zoom in to just one of these sections, and we can treat these new sections as brand new photos. And we can run our algorithm on just this section. If we take the chi-square distance for just the pixels that have a pattern value of 254, the ones that are still highlighted in green, then we get a total distance of 4.48, which I know sounds small, but keep in mind that the original image had a distance of just 6.06, and that image had almost 50 times more pixels than this sub-image. This 4.48 carries a lot more weight here, distance-wise. If we try to get the histograms containing all the patterns in these two new photos, we get these histograms. And if we calculate the distance between them, we get a total distance of 299.77. By finding the distance like this, we have forced our algorithm to compare the patterns in the same part of the face. For comparison, let's consider the same region from the photo containing the same person, the one whose distance was incorrectly greater before. If we just compare this section by comparing their histograms, we get a total distance of 203.79, which is smaller than the section from the photo of a different person. This seemingly fixes our problem from before, since the same person now has the shorter distance here. If we go back to our photos and divide them into a 7 by 7 grid of regions again, we can find the distance between each pair of regions. This is the first improvement we can have to help improve our accuracy. We have these regional distances, and we can just add them together to get a total distance between the two images. The second improvement we can make is actually much simpler. We can weigh these regions differently depending on how important they are. And the reason this change is effective should be obvious. The region which doesn't have any face should not be considered at all. And the section with the eyes should probably be given more weight than some of the other sections, as it has a little bit more complexity to it. Now, with my test and sample set images, I played around with the weights for about 10 minutes, and eventually I settled on these weights, giving me a good accuracy. I definitely could have tried to find the most optimal weights for this, but I found it sufficient to find them by intuition and with a tiny bit of trial and error. Here, the weights simply mean to multiply the distance attained from that region with this weight before adding it to the total distance, which of course affects the overall sum. If we apply these weights to each region for this photo and add up all these weighted distances, we get a total distance of 15,273.99. And if we look at our photo whose distance was incorrectly higher, despite being the same person, and now calculate the distance using weighted regions, we get a distance of 13,485.12, which is now lower, which is a great success. And to help visualize this process, we can give the regions a shade of color instead of a number, depending on the distance for that region. We can shade the region green if the region has a smaller distance, and we can shade it red if it has a larger distance. And this should now look familiar to you, as this is exactly what was running at the beginning of the video. If we take our new algorithm and apply it to our earlier experiment, now using weighted regions, we now get correct matches for 21 of the 25 photos, shooting our accuracy up to 84%, which is much better. I really tried to get a higher accuracy, as I really wanted to see something like 90%. I tried adjusting the weights. I tried looking for maybe like the 3 closest photos instead of just the closest, but 84% was as high as I could get it without cheating with the data. But 84% accuracy is actually pretty good when only using photos from the wild. For comparison, Facebook's facial recognition software also uses photos from the wild, and their accuracy is 97.35%. But hey, I'm not a multi-billion-dollar company, and to be honest, I'm pretty proud that I was able to do this well without the help of any libraries. And hopefully this video empowers you to do something similar. And if you feel like this video has helped you understand facial recognition, or if you've enjoyed this video and you want to see more like it in the future, it would mean a lot to me if you could like, comment, and subscribe. When people do that, it tells me I should make more videos like this, and it also helps my channel grow. Thank you so much for watching, and until next time.